In this section, we're going to start out by solving triangles. And when we solve a triangle, that means we're going to find any of the missing lengths or angles that are not given. For now, we're going to restrict the problems to right triangles, but later we'll be able to solve any triangles. We won't have to necessarily have a right triangle. Alright, so when we label the triangles, there's two ways we can do it. The textbook uses like the sides are A, B, and C, and then the angle across from it is angle A. The angle across from side A is angle A, across from side B is angle B, and then C is of course across from the right triangle, but we can also call that angle C. And then we can also refer to the vertices as A, B, and C as well. In class, or well, we don't really have class, this is online, but for lecture, what I like to do is use Greek letters, because when I say A, B, and C, and then this is also A, B, and C, it gets confusing, and then I have to remember to say angle in front of, you know, the capital A, B, and C every time, which I know I'll forget. So I am going to, we'll still call, you know, the sides little a, B, and C, but then this angle across from A, I'm going to use alpha. And then the angle across from B, I'm going to use beta. And then the right angle, later that won't need to be a right angle, but I'm going to use gamma for that. So that would be gamma. Okay. So we're going to assume that C, angle C, or gamma is our right angle. That's like C will be our hypotenuse. So in this problem, C is over here. Beta is 12.4 degrees, so let's just say this is beta. And then B is 3.6. So we need to find A, which means the side A, and we need to find alpha. Oh, and C. A lot of ands there. Okay, so because we know beta, and then gamma isn't directly given, but we know this is a right triangle. Solve the right triangle. Not given, but assumed. Gamma equals 90 degrees. Okay, and of course we can call that angle C also. Use a capital C if you do that. Alright, so we actually do know two of the angles. We can find the third. So this implies alpha will equal, of course all three angles need to add up to 180 degrees, so we'll subtract from 180. Or you can just, of course, subtract from 90, given that these two have to add up to 90. They're complementary. But since I started with 180, I'll just leave it. Okay, so 90 minus 12.4 is 78 degrees. So alpha equals 78 is the first part of the solution. Now to find, so we don't need any trigonometry for that, of course, but we do need trigonometry to find A or C. You can decide which one you want. Beta was given as 12.4, so I'm going to use the fact that it doesn't really matter which one you find first here. You can do sine of beta is 3.6 over C, or tangent of beta is 3.6 over A. So let's do that. Tangent of beta is 3.6 over A, or in other words, tangent of 12.4 degrees is 3.6 over A. So A is 3.6 over tangent of 12.4 degrees. And I'm going to have to switch to degrees because we were working in radians last time. Okay, so of course I just multiplied by a and then divided by tangent of 12.4 to get this expression. So 3.6 divided by tangent of 12.4. Didn't really need that parenthesis. 16.4. Now I'm rounding to one place because these are to one decimal place. So I'd round to the same. Oh, except I said to round to 2. So we'll round to 2. But if you're not told, I just round to what's given in the problem. 16.37. So A is approximately equal to 16.37. There's our second part. Now we find C, which of course we'll use the Pythagorean theorem for. So that's 3.6 squared, well that's actually B, but that's okay, plus 16.37 squared. Here, let's make that C and then take the square root. So C is approximately, now when I plug this in, I'm actually going to use this number because that's more accurate. So square the answer plus 3.6 squared. And I forgot to hit the square root, so I'll do that now. About 16.8 or 16.76. And of course, C has to be the longest side. B is really small and A is really big. So that's why A is so big compared to B, right? My picture is obviously not at all accurate. This should be a lot, the height should be a lot smaller compared to the hypotenuse and A. That's okay. You get the idea, right? Okay. That's the only one of those I'm going to do because I think they're fairly easy. And later, we'll spend a lot more time with problems when this angle is not a right angle. When we have A, B, or alpha, beta, gamma, none of them are right angles. Okay? All right, let's do these applications. So a 200-foot cliff drops vertically into the ocean. If the angle of elevation from a ship to the top of the cliff is 22.3 degrees, how far offshore to the nearest foot is the ship? We've actually done an application similar to this before when I talked about angle of elevation and angle of depression. So this really isn't too new. I think most of you can already do this. So we have this cliff and then we have the ocean, right? And there's a ship out here, and we know this is a 200-foot cliff. And then if we're sitting on the ship and looking at the top of the cliff, the angle of elevation is 22.3 degrees. So this is our line of sight. Go this way. Right, and we're looking this way. So we are talking about this angle being 22.3 degrees. Remember, angle of elevation and angle of depression always are measured from the horizontal. We talked about that. So the horizontal would be the water, and then up to our line of sight, that's the angle of elevation. Say you could see a fish down in the water, then this would be the angle of depression right here, right? So always measure from the horizontal. I'll just abbreviate horizontal. Okay. So now we want to find how far offshore we are. So let's call this D. We want to solve for D. So if you just label in a diagram what variable you're looking for, that's good enough for defining the variable. Let's solve for D. Of course, we're going to have to assume this is a right triangle for this to work. So we have from the point of view of this angle, this is the opposite, and so let's use tangent. So the tangent of 22.3 degrees is 200 over d. So if I multiply by d and then divide by tangent of 22.3, d is 200 over tangent of 22.3 degrees. Alright, so let's see what we get. Of course, we need a calculator for that. So d is approximately, we're going to round to the nearest foot, so that'd be 488 feet offshore. I should say the ship is approximately 488 feet offshore. Okay, let's do one more and then I'm going to take a break. Alright, here in this problem, a hot air balloon is rising vertically from a point on level ground 120 feet from the point directly under the passenger compartment. So right under the balloon, I'm talking about the point on the ground, right? The angle of elevation to the balloon changes from 19.2 degrees to 31.7 degrees. How far to the nearest tenth of a foot does the balloon rise during this period? Okay, so let's draw a picture. We've got, I'll put it over here, this balloon, right? And it's rising, of course. And from a point under the compartment to a point on level ground 125 feet away. So this is 125 feet. The angle of elevation of the balloon changes from 19.2 to 31.7. Okay, so that means the balloon is rising. Here's our angle of elevation. If the balloon is up here now, the angle gets larger. So say this one is 19.2 degrees, this larger one is 31.7 degrees. Okay, so we want to find this, how far it rose, so we want to find this distance. Okay, so we know this side and we know these angles, and notice this is a right angle, so we have two right triangles here to work with. Now again, we have angles and opposite and adjacent sides of those angles. Now the opposite sides are unknown, but I'm using that because that's where D is at. Alright, so we're going to use tangent again. Now we don't know anything about this whole length, and we don't know anything about this length, but if we can find, this length and this length, we can subtract to get D, right? So let's use, let's call this, so for the smaller triangle, let's call this side X, and for the bigger triangle, then this side is X plus D. Okay. Or you might want to just call that Y and say that D is Y minus X. Oh, I'm sorry, I'm off the screen again. It's up to you, but so this is X, this is D, then this entire length is X plus D. Or maybe you would just want to call this Y, and then D is Y minus X. Maybe I'll do that. Let's call that Y. Alright, so then note D equals Y minus X, right? And we want to find D. We already said that right there, find D. Let me zoom out. And I zoomed in. There. Okay, so tangent of 19.2 degrees is x over 125 degrees, that we know, and tangent of 31.7 degrees is y over 125. Why did I put degrees there? That's feet. We don't need to put that label in there. So if I know this relationship, see, I can find x and y, and then use that to find d. So d equals y minus x, which equals y equals, using this, y equals 125 tangent of 31.7 degrees. Here, I'll write that down. 31.7 degrees. And likewise, x equals 125 tangent of 19.2 degrees. Or you can factor the 125 out. So tangent, 125 times the tangent of 31.7, make sure you close that parenthesis off, minus tangent of 19.2. That is approximately 33 point, I said nearest tenth of a foot, so 33.7 feet. So the balloon rose approximately 33.7 feet. So we use the numbers that are given to find the distances, the heights of the two triangles, and then just subtract to find how much the balloon has, or how far the balloon has risen. Okay, let's take a break here.